Now let's talk about how to do these depth-oriented traversals without recursion. So the traversal logic is still going to remain the same, but instead of using recursive method, we'll try to have an iterative method. So let's start with the pre-order traversal. So if you remember, the recursive logic was that if I want to do the pre-order traversal given a particular root node, the idea was to perform check if my node is null. If it was null, then there was nothing to do, we would return. That was the logic. And otherwise we would do the node specific action of this traversal, and then we would do the pre-order traversal on the node dot left and pre-order traversal on node dot right. Okay, so this is our recursive logic. Now let's try to reframe this logic in an iterative manner. So now I'm going to have the pre-order traversal iterative, and this also receives a particular node as input. And the first thing that I should do is check if the node is null. Okay, so if my node is equal to null, in that case simply I would return. Okay, so it might be a tree with no node at all, so then there is nothing to do. Okay, so this is identical to the logic here. Otherwise what I should do is I have to somehow emulate the recursion stack here. So what I will do is I will say that I have a stack S, okay, and then I will say that S dot create new with capacity equal to so let's say current tree has certain number of nodes, so at the most we'll be pushing all nodes of the tree onto this stack. So let's say we require a stack of size equal to tree dot capacity, tree dot node count. Okay, so that's the new stack that I have created with certain capacity of my stack. And first thing that I'm going to do is I'm going to push my node onto the stack. So I would say s dot push node onto the stack, and now I'm going to start executing. And how long will I do? Till I have something in my stack to do. Okay, so now I will need a looping construct because I have to do something till my stack is empty. So while I would say that s dot is empty is not true. Okay, so this is the negation. Okay, while my s is not empty, what I would do is I would say that my current node is equal to s dot pop. So I have got a node from my stack, and first thing I will do is I will perform the node specific action which I was doing here. Okay, and once I do that, then I have to push my left and right. Okay, so in case of recursive logic I was giving first call to the left and then I was giving call to the right, but here we need the exact opposite order because we are pushing things onto the stack. So I will do current dot right, I will take it and I will push it onto the stack, and then I have s dot push, I will take current dot left. So the right goes below and on the top of it comes the left, and then I'm done. Okay, and then the extra thing I should do is I should check if these are null. Okay, so I should put a condition around it. So only if they are not null. Okay, if they are not null, only in that case I should put those nodes onto the stack. Similarly here I should add a condition if they are not null. Okay. Okay, so push current dot right onto the stack if it is not null, push current dot left onto the stack if it is not null. Okay, and that's how you have sort of emulated the logic of recursion in the iterative manner. Okay, so let's see how it works for the same tree that we have been working with, this particular tree. So let's draw that tree here. We have 10 and then we have 20, 30, right? So there is 20, then there is 30 and 20 has 60 and 50. There is 60 and then there is 50 and then 30 has 40 and 70. Okay, 40 and 70. Okay, and now I'm going to start the execution of this function with 10. So I would say that pre-iterative with 10. Okay, and what will happen is I will check if my node is null. So is the address of 10 null? It's not. That's fine. So I'll create a stack, and stack of what size I will create? 1, 2, 3, 4, 5, 6, 7. Okay, so what will happen is s dot create new of size 7 and the stack will be empty. Fine. And then I would do s dot push 10. So let's visualize our stack here. So I have stack and I have pushed 10 onto it, and it has at the most 7 slots, right? So I have 1, this is 2, 3, 4, 5, 6, and then there is 7. So let's number these slots: 0, 1, 2, 3, 4, 5, and 6. So that's my stack S. And now we have pushed 10 onto it, and now we will enter this looping construct. So while our S is not empty, so currently we have pushed one element, so S is definitely not empty. So now what is going to happen is I'm going to have current equal to S dot pop. So let's keep track of our variable current. Okay, so I'll keep track of our variable current. Currently current is our 10. Okay, and now 10 is removed from my stack. Now my stack is empty. Okay, and now first thing I have to do is my traversal specific action, and let's say what we are going to do is we are just going to print. So let's keep track of the output here. So my output is 10 right now. Okay, and then I'm going to push current dot right if my right subtree is not null. So for 10, right subtree is 30 and it is not null, so I'm going to push 30. So I'll have 30 here, and then I'm going to push current dot left if my left subtree is not null. So for 10, 20 is the left subtree and it is not null, so I'm going to push 20, and that's where I finish this loop. Okay, and I have missed one closing braces for the whole function, right? That should be here. Okay, so let's start back. So now I'm done with, I have reached the end of the loop. I'll go back to the beginning. I'll ask question, is my stack empty? No, it has 2 elements. So I'll come inside, I'll pop the element which is 20. So 20 is gone from the stack, and now my current becomes 20. And then I will do the node specific action, which is simply currently printing the node. So I'm going to print 20, and then I'll ask question if my right subtree is null. If it is not null, then I'm going to push my right subtree. For 20, the right subtree is 50. It is not null, so 50 is going to come at this place. And then I'm going to push left subtree if it is not null. So for 20, the left subtree is 60, so I'm going to push 60 here. Okay, and then I reach end of the loop. I go back to the beginning of the loop. Is my stack empty? No, it has 3 elements, so I come inside and I pop an element. So now 60 is gone from the stack, so my current becomes 60. Okay, and then I do the node specific action, which is printing. So I print 60, and then I ask question, is my left subtree null? It is null. In that case, I will not, sorry, first I will check the right subtree. Is my right subtree null? It's not null, so I won't push it. Then I will check if my left subtree is null. It is null, so I will not push it. So now there is nothing to do. So I come back and I ask question, is my stack empty? It is not. There are 2 elements still in the stack. So we go inside the loop and we pop an element. So now 50 comes out from the stack and my current becomes 50. I have to print 50 because that's the action I'm doing, and then ask question about the right subtree of 50. It is null, so I will not push. Left subtree of 50, it is null, so I will not push. I reach end of the loop, I go back to the beginning of my loop. And is my stack empty? It's not. I still have 30, so I'm going to pop an element and my current becomes now 30, and first thing to do is print 30. So I will print 30. Ask question about right subtree of 30. Is it null? Well, it is null, so don't push it. Then ask question about the left subtree of the current. Is it null? It is not null. In that case, we are going to push 40 here. Okay. So now we have reached the end of the loop. We go back to the beginning. Ask question, is my stack empty? Well, our stack is not empty. We pop an element. So 30 is gone. And now my current becomes 40. And similarly, the 40 will be gone from here because we have popped it. Okay, so 40 is gone. And once my current becomes 40, I have to execute this block which says just print the element and then ask question about right subtree of 40. It is null, so don't push it. Then ask question about the left subtree of 40. It is 70, so go and push it. So I will have 70 stored here in my stack. I pushed it and then go back to the beginning of the loop. Is my stack empty? It is not. So go and pop an element. So 70 comes out and my current becomes now 70 and then print 70. That's what is required. And 70 has both right subtree and left subtrees as null. So I will not push anything. I reach end of the loop. I go back to the beginning of my loop and ask question, is my stack empty? Well, the stack is empty. So we reach to the end of our function. And that's how the iterative preorder traversal works. And let's compare it against the output that we received for the recursive version, right? Preorder traversal. This output should be same. There should be no difference. Okay. So let's compare these two outputs. We have 10, 20, 60, 50, 30, 40, and 70. So we received identical output because it's still the preorder traversal. Okay, so no matter you use recursive logic or you use the iterative logic, output should not be affected. What might get affected is the efficiency in terms of how much memory you consume and actual clock time. So your iteration might be faster than the recursive calls, but it should not affect your output. The time complexity still remains the same. It is still theta n in this case as well as this case. So that's the iterative preorder traversal. So now question to ask is, think about this. What will be the scenario when we will require this complete stack? You notice that the stack had 7 elements. We created a stack with 7 slots, 0 to 6, but we never really required it. So can you think of a scenario when we will require all the slots in the stack? Think about it. Okay.